Good day there. Welcome to basically the last day of Trig, really, or the last kind of new stuff, even though what we're going to go over today, the math behind it isn't anything new. It's all still the same thing that you've been doing for the last few weeks. You got angle and a radius and your x and your y values. It's just a little bit different way of writing that. The stuff you've been going over for these past few weeks is all very much the same. We've been working with vectors, your magnitude, that's the same as the absolute value of a complex number. We're going to do the same thing today. It's just referring to it as something a little bit different, not just the radius, even though we might have done that. The direction of a vector, the direction of a number, the angle that we're going to find now, it's all the same thing. They're just slightly different contexts that they would be in that would be referring to them. It's just the way you refer to them. So the math is still the same. So some of this is probably kind of going to be a review over things, but we're going to look at today what's called polar form of a number. Very much the same math as we've been going over before. So generally what you guys are used to plotting numbers in Cartesian or rectangular form. And that's where we have an X and a Y. It's called that because it makes a rectangle. And when you have a Cartesian plot, like if you have a map or something, you follow, go this way, this way. If you look at like a road map, that's called a Cartesian map. It's usually got, instead of X's and Y's, it has like A through, M or whatever, and then numbers along the other side. But it's still using the same type of idea that you basically make a rectangle or a grid out of something and find a position on that grid. Polar form finds the same spot, but in a different method. They use a different method to find that spot. So here for polar form, what we do is we use a radius and an angle to find that spot. So we used a lot more navigation and things like that as we kind of went over some of that stuff. Okay, so we're kind of in essence here turning about a point, and then we'd walk out from that point. So here we'd turn so far, angle and standard position, and then we'd walk out from that point, perhaps going to a certain spot. But that's our radius and our angle. Same stuff that we've been going over, just in a little different format. So I'm going to go over a couple examples about how we would change between the two so we get the same spot. But, if that makes sense and you want to jump to it, go ahead right away. But the basic steps, we're going to go over one example of each, Cartesian to polar and polar back to Cartesian. And so Cartesian to polar form, Cartesian again being rectangular form. Just like we did with our number, complex numbers, vectors, we use the arctangent to find the angle and then maybe having to make an adjustment, from 180 or 360 if we have to. And then we use Pythagorean theorem to find the radius. Nothing new, same type of stuff. So I did put up here a slide as well, just in case some people had questions about how we'd adjust that angle. It depends on what quadrant you're in. If you're in quadrant 1, you don't have to make any adjustment to the arctangent. It's just whatever it tells you that it is. Boom, that's the angle. If you're in quadrant 2, you do have to take that away from 180 degrees because you are coming back up that certain amount. Quadrant 3, obviously you have to add to 180 because you're going down in that quadrant 3 area. And then here, arctangent, because the reference angle is in here, we got to take that away from 360. Okay. So let's look at an example of how we might do that. So here we're going to convert this coordinate, -8, -3, into polar form. If you want to, you don't have to do this part at all, but I'm just going to show you that connection so you can see that. You can use Desmos to estimate this. So I'm going to show you how to do that, and I'll put a link to that right on this page here too when we're all said and done. But here is the point -8, -3. Okay, so we can put that in Desmos. That part makes sense to us. But Desmos also has a thing. There's an option tab up here, and notice we can change the grid from Cartesian form or rectangular form, or we've got all these rectangles, to polar form. But notice as we switch there, the point right here doesn't actually move on the page, just the grid switches behind it. So the point is still in the same location, it's just how we find it is a little bit different. So here, if I were looking at this to make an estimate, I'd say, well, each of these circles represents one spot away from the origin. So here we're about 1, 2, 3, 4, 5, 6, 7, 8, oh, no, 9. I must have missed one in there. Between 8 and 9 is about how far out this point is. And then we can also use these angles here to estimate about what's the angle. It's somewhere in between. I think this is what it must be, 195, and here's 210. So maybe it's at about 200, I don't know, somewhere in there, right? 200 degrees around. And to check that, you know, we can get a little bit more here. I can say, well, my radius, oops, we got to use lowercase r for radius, is equal to, I don't know, somewhere in between 8 and 9. I'm going to say 8.5. All right, that looks pretty close, right? I mean, maybe it'll end up being 8.6, maybe something like that. But that's pretty close there. And now you can also add in things. Now we can't put the bounds in there. That's actually what I thought first, but we have to put these curly brackets after it. Now what I can do is 0 less than theta, right? Theta again is an angle, so I'm saying 0 is less than theta, and then we're going to go up to, well, just to show you how this kind of works. Here this is going to go from 0 out to 270 degrees because I put that in there. Actually, I wonder if I can just put it right here. Yeah, cool. It does let me do that. Nope. Don't let me do that though. So you can make it go up to 270, and there it stops from 0 to 270. If you wanted to do other stuff, like we could go from 30 to 270, but I want it to start in standard form, so I'm going to go from 0. And it's got to be somewhere in between 210 and 195. Now I could sit here and kind of guess, like, maybe it's 190. Oh no, maybe it's maybe it's 200. Oh, 200, pretty close, right? Now, if I didn't want to guess, I could always put a slider in here. So I could type in A and add a slider and say, oh, let's let this big angle be somewhere between 195 and 210, right? And now I could slide this angle along here, and you can see the red line kind of move as I, adjust the end angle and say, okay, probably somewhere around 200. So I know that this point approximately should be somewhere around 200. So let's grab a copy of this so we make sure that it's in here. Oops. Let's put it that way. So if you want to use Desmos to do that, you certainly can. I will hyperlink that right to itself. So if you want to click on this and follow that Desmos thing, it might take a little bit to actually get it to pop up, or you can copy and paste it right in there. So we know this part, right? It should be about 8.5 comma about 200, right? That should be what we get as our end result. So the actual calculation in here, what I would do to figure out exactly what those things are, first I got to figure out the radius, and that's going to be just a Pythagorean theorem. We can make a little right triangle in here. Actually, I should just put one right in there so we can see it. Nope, that's not quite what we want. Let's on either. Let us flip this thing over. Okay, so there's our kind of triangle. We have 8 this way, 3 this way. So we could find that radius, right? I would know that the radius is equal to the square root of 8 squared plus 3 squared. Now, some people might be saying, well, aren't they negative? Which is true, right? They are negative, but when you square a negative number, it's the same as squaring a positive number. It's not going to make a difference. So instead of putting those negatives in there, I'm going to put that. And I doubt that this is going to work out exactly. You can leave it in square root form if you want to. I'm just going to go ahead, 64 plus 9, 8.54. So pretty close, right? We had estimated that using Desmos, right? Again, we had estimated that that was going to be about 8.5. The actual calculation, the square root of whatever we had there is about 8.54. So pretty darn close, right? And then when we find the angle, right? When we find the angle here, that's going to be, well, we got to do the arctangent of well, we've got our opposite side here. Let's bring this down for a second. Our opposite side is 3 compared to 8. So we'd say that's the arctangent of 3 over 8. And we're in the third quadrant. So it's got to go 180 plus whatever number we get. Because again, arctangent's only going to tell us the small angle in here. We have to do that extra adjustment. So I've got to do 180 plus that stuff. And then again, I would use my calculator here. Let's do 180 plus the arctangent of 3 over 8, bada boom. And oops, I better make sure I have degrees turned on. There we go, about 200.54. Well, 200.54 degrees. So there's our adjustment for finding the angle, right? We've used that little bit of adjustment, which is exactly what we were finding in here, about 200.5. Boom, right? I mean, we could make this a little bit more, add our little decimals on there, and that's going to be pretty darn exact. This red line gets right there. But that fits with our estimation. So we would say the final answer to this, our actual coordinate, oops, we don't want all that, u would be 8.54, or you could put the square root of 73 if you wanted there. That's fine. 200.54. All right. Yep. Or 5. Oops. 6. Made a mistype in there. I was looking at my calculator, rounded down instead of up. Oh, all that happens, right? And so there we have that part there. Okay. 200.56 actually in that case. So that's the pieces in there. Okay. We have those things. Let's see if it picks all this stuff up. All right, let's change this actually to 6 so that we have that right. So that's converting, right? It's the same math you've been doing. It's just in a slightly different format. So it shouldn't be anything too extreme. All right, I know I put an absolute value there. I'll go back and fix that stuff. But that's not too bad there. This is the final form in that case. All right, so that's that example going from Cartesian to polar. That's what we just did on the angle and did that. Now we're going to go the other way, going from polar back to Cartesian form. And actually, I find this a little bit easier to calculate because the steps aren't quite as much. You don't have to do quite as many steps. But in here, if we look at this, like again, this would be the whole thing. We have an angle, radius, x and y. If we use our trig to sort of piece that stuff together, I mean, here the y value is related to the radius by sine. Sine of the angle is y over r, right? I mean, that's what we would have. We'd have sine of theta equals y over r, correct? Not 4. Which then means that we could solve that by multiplying the r over. Right? We could just do that. Right? And here, that's the key piece. This bottom one, that is the key thing for finding that value. So I'm going to put a little box around here and let's make sure that, yep, we're going to emphasize that situation on there because this is the important one, that y is equal to r times sine theta. That's all you have to do. You don't have to do any extra conversion. It will directly tell you exactly what that point is going to be. And then for the x value, well, that's adjacent and hypotenuse for the r value, right? So this would be just x over r, and we'd have to change from sine to cosine, right? And so in here, we'd change from sine, oops, let's update that, cosine, and that tells us the x value. And that's it. That's the whole kit and caboodle right there. That's all we need to have. As long as we have these two equations, that's all we have. Done. So let's go in here. We're going to do one more example on this one. I'm going to use Desmos to estimate so you kind of see how those two things are related, and then we'll do the actual calculations here in a sec. So this one is 5 and then 294 degrees. So it's in polar form. So we're going to change that back to Cartesian form. So again, I'm going to go ahead and look at where exactly that is. So that means we have a radius of 5 in this case. Actually, let's just make a new one here. Actually, no, it should be fine. It'll save it that way. So anyway, in here, it should be 5. That's our radius. So we're right here on 5. And we're going out to 294 degrees. Oops, let's make this. There we go. Now I got it updated. I have to actually have it in this part. If you change it here, this won't matter so much. But so here's out to 294. It's sitting about right there. And again, this is in our kind of Cartesian, or sorry, our polar form. I'm going to switch it back to Cartesian grid. So there it is. See, it's still the same radius. Nothing moved. It just changed the background. So here I noticed, well, it's over about 2 and then down maybe negative 4.5, something like that. So I know that this is at about 2 comma negative 4.5. That's got to be about where that spot is, right? It's got to be close to that. And so I know that that's got to be about, it's probably a little bit off, right? I mean, there's probably going to be some estimation that is off on there, but that's okay, right? So I'll put this down here if you guys want to explore that yourself, you can. So then you can kind of click on that or copy and paste it right into there, and the same picture should pop up. But in here, to do the actual calculation, again, okay, so let's find here, I'm going to find the x value first because that's usually, x comma y. So we'll find x first. Should be the r value, 5, times the cosine of the angle, 294, right? And that's not going to work out to be anything exact. I'm going to have to use my calculator, but I don't have to do any converting. That's the very beautiful thing about using sines and cosines. I'm sitting here dancing because I don't have to do anything extra. When I type that in my calculator here, it's 2.03. Oops, not 3.4, just 3. Yep, 2.03. I know there's extra stuff, but that's what it rounds to. Rounded 2 decimals. There, we're good, right? If we want to find the y value here, then we would use 5 times sine. That's it. 5 times sine. I don't have to do anything super complicated. 5 times sine, 294. Boom. And it's, ooh, nice. Negative, let's update what that's approximately to. Negative 4.57, which was pretty darn close to exactly what we had found before. So I'm going to move these up here just a little bit so we can see how we did that. And so then we put our final result in there, right? We put our final answer in as we want to put it in a coordinate form. So our final answer would be that we are at 2.03 comma negative 4.57, right? There's our final result. Now it's back in Cartesian form, which, as we know, this is very close to exactly what our estimate was. If I wanted to get this a little closer, 2.534, 5.7, boom, now we can see, oh yeah, it's really estimated very, very closely there. But like, that's how you can get those estimates. Again, you don't have to use decimals if you don't want to, but it can certainly help if you're kind of checking to see, does all that stuff work out? You can do that as well. So again, if you guys have any other questions, again, nothing really new in here, just, different application, a different way that we write that. So if you guys do have questions, let me know on there. The next couple of days, what you guys have is kind of some review stuff on there. Otherwise, that's pretty much the end. Just make sure that you're getting your stuff in by Friday night, because then I got to put all those grades in. And other than that, you guys take care and have a wonderful summer, and hopefully things go well. Talk to you guys later.